Hey, welcome back to Guillotine to 18th Century Chemist Theater. Today we are going to talk about Avogadro's law, the humble Amadeo Avogadro of the Avogadro's number fame, which, remember, he never came up with, but he came up with the concept of equal amounts. And so we're going to show you what his law is, and also show you how to create an even better combined gas law that for some reason no one ever teaches you except for me. And so Avogadro, in leading up to the idea of the mole, came up with a very simple idea that the volume of a gas is proportional to the amount of the gas. Which eventually led to the idea that no matter what the identity of an ideal gas is, remember real gases vary a little bit, but the identity is really irrelevant to how much space it takes up because there's so much space in between them. And so as the number of molecules or moles go up, the volume goes up. And again, think of a balloon. When you blow in air, the volume goes up because you've got more gas in there. So it's a very, very simple idea. Now, the problem is that we don't often run into situations where the amount of gas is changing because remember that the only way the amount of gas is going to change in most problems is maybe some kind of chemical reaction. Otherwise, all things aren't really being held equal. But the basic principle, if you forget nothing else about Avogadro's law, is that from an ideal point of view, all gases take up the exact same volume. Notice that it doesn't matter what the gas is. And if you go with STP, at least old STP of 1 atmosphere, remember that the idea of STP being 1 atmosphere has sort of been outdated since, I guess, the 80s. But if you look it up, everybody still talks about STP being 1 atmosphere. But anyway, so if we assume we have 1 atmosphere instead of 1 bar, any gas at the old STP will actually take up 22.4 liters. And that's a really great shortcut if you're ever dealing with the old standard temperature and pressure, which is most of the time, that any gas, 1 mole of any gas, in an ideal sense, will take up 22.4 liters. So that might be a nice shortcut for you. So let's look at a somewhat contrived example of Avogadro's law. Oh, there goes our friends. Some amazing animation there. So this is taking the very simple principle of Avogadro's law and then saying, well, how can we spice this up a little bit? And so we're taking atmospheric oxygen and converting it to ozone. And that's a good example of something actually changing the amount of moles. And I'll show you what that equation is. Anyway, so if we have 1 mole of diatomic oxygen and convert it to ozone, what will the new volume be? Well, we'll be changing the amount, and so we'll be changing the volume. And so the trick to doing this problem is realizing that the amount is changing, and how does the amount change? I don't give you what the moles change to, but if you say, well, 3 O2s are going to become 2 O3s, which sounds very simple once you see it. But the trick to Avogadro's law problems often will be knowing how the amount changes. So you could actually tie a stoichiometry problem into this, or a lot of things. So there's a lot of neat high-level tie-ins. But anyway, notice that I gave myself descriptive subscripts here. I said instead of V1, V2, I said O2, O3. And you can't subscript a subscript there, so that's what we have. Anyway, so we are going to be looking now for the idea of the volume of ozone. Since, again, we now know the ratio of moles of each. And so to get the moles of ozone, I start with my 1 mole of O2, and I do a very simple stoichiometry problem, a mole-mole ratio. And I say, okay, for every 1 mole of oxygen, I get, for every 3 moles of diatomic oxygen, I get 2 moles of ozone. And so very simply, I guess most of us can figure out that'll be 2/3 of a mole, or if you're looking at sig figs, it'll be 0.667 moles of ozone. Once you have that, this is a pretty simple problem. All right, so I'm going to solve for my volume of ozone. And as you might suspect, it actually went down because as the moles of gases went down, it would take up less space. If it's in a container, again, all other things being equal, which means pressure didn't change, temperature didn't change, and of course those things are open to change. Anyway, there's Balloon Boy and the dog. So anyway, so here we go. The super combined gas law. I don't know why you don't see this anywhere, but there's no reason that, and here we go, we can combine these together. There's no reason we can't put amount into the combined gas law. Now, I guess most people don't because amount usually isn't changing. But, and again, I challenge you to find this anywhere else. Here's the super combined gas law. I'll let you in on the secret. Now, not only can you derive Boyle's, Charles, Gay-Lussac's, you can also get Avogadro's law out of there. They're all there. Now, again, if you're holding N constant, which is most of the time, then you just get the regular combined gas law. But now you can actually deal with changing molar conditions too. Now, are you going to run into them often? Maybe not, but there you have it. So there you go, my patented, trademarked super combined gas law. You're welcome. You're welcome. So, I think we only have one lesson left. I think we have to talk about gas stoichiometry, and then we're going to wrap up gases. And so I'm looking forward to that. So, thanks for watching, and have a great day.